I mean base 10. Now this problem turned out to be a little bit more popular than I thought. We're talking about a base 10 number, and it looks like an absurd question. Okay, again, base 10 means decimal. Base 10. Now, if you read the question, it says, are there any two-digit decimal numbers n such that 1/3 of n equals the digits of n reversed? Now, just to put this in context, I just finished a problem that turned out to be rather popular. I was surprised. If you consider the number 51 in base 7, you know what this means is 5 times 7 plus 1 if you expand it out. But it turns out if you divide this by 3, which is a base 7 digit, okay, you actually get that this is equal to 15, which is the reverse, right? Is equal to 15 base 7. Okay, and this is not hard to see. I like doing the arithmetic in decimals. So 5 times 7 is 35 plus 1 is 36 divided by 3. So you would have this is equal to 12. Right, folks? Now again, the work here just in the name of space. 5 times 7 is 35 plus 1 is 36. 36 divided by 3 is the 12 you see right here. This is understood to be base 10. But notice that this is equal to, and I'll write this for emphasis, 1 times 7, the base 7 digit right there, plus 5. Okay? So you see this is definitely an example of where the problem statement is true in base 7. Okay, base 7. Okay, so it can happen. It happened in base 7. So the question is, are there any two-digit decimal numbers in such that 1/3 of n equals the digits of n reversed? Okay, so let's go down. Now, so we'll call n 10a plus b. All decimal digits are between 0 and 9 inclusive, right? So, but in this particular case, we have to stipulate also, just as a slight exception to what I wrote down, a is not equal to 0, or it wouldn't be a two-digit number, right? Just a detail. I wrote a is possibly equal to 0, but a can't be equal to 0, or this would just be n is equal to b, a single-digit number, right? Okay, so let's keep going. Now, notice this is a direct translation of the problem. N is our number, right? So we're saying that n divided by 3 is equal, see how these are reversed, AB, AB, BA, BA right here? Okay? So if this can happen, then this equality must hold for some choices of A and B. So let's see what happens. Now again, y'all, this part right here is very straightforward. What I did was just multiply through by 3. Now notice that this would imply that 7a is equal to 29b. And you'll note that 7 and 29 are prime numbers. Not that that's necessarily important here. But notice that this statement right here, you subtract b from 30b, you get 29b. If you subtract 3a from 10a, you get 7a, right? So what does this tell us? Since, actually it is important, 29 and 7 are relatively prime. They're not only prime numbers, but they're relatively prime. And so that would imply that a would have to be some multiple of 29. And we'll say 29m. But you can see that this definitely is a contradiction, right? In other words, we know that the decimal digits, so that's why this was important. Write down all decimal digits are trapped between 0 and 9, right? And so a cannot be a multiple of 29. Like if m were 1, that would be a is equal to 29, right? We know that a can't be equal to 0, right? So you see how this is impossible? Possible, which says if this arithmetic that we've gone through holds, we get this absurdity that we get A is much longer than the digit bound, much larger, excuse me, than the digit bound that we have right here. So to answer the question, my dear viewers, is an emphatic no. Okay, owing to this absurdity based on the digit bound. Okay, is it all on the same screen? Sort of. Okay. Thank you all for viewing.